Have you ever looked up at the night sky and felt small? It's a common feeling. We see countless stars, each one a sun, perhaps with its own planets. These tiny points of light are incredibly far away. So far, in fact, that the light we see from them tonight left those stars many years ago. Some of them left before you were even born. This vastness of space presents us with a huge problem. It's a problem of time and distance. Our universe is so big that even light, the fastest thing we know, takes a very long time to travel between stars. This cosmic speed limit is a fundamental rule of our universe, set by Albert Einstein himself. Nothing with mass can travel at the speed of light, and nothing can travel faster. As an object with mass gets closer and closer to the speed of light, it requires more and more energy to accelerate it further. To actually reach the speed of light, it would need an infinite amount of energy, which is impossible. This rule keeps us locked in our own solar system. Our fastest spacecraft would still take tens of thousands of years to reach even the nearest star, Proxima Centauri. That's a journey far too long for any human crew to undertake. This speed limit feels like a cosmic prison. It means that all the wonders we see through our telescopes, distant galaxies, beautiful nebulae, and potentially habitable exoplanets, are forever out of our reach. We are like someone standing on the shore of a vast ocean, able to see distant islands but with no boat fast enough to get there. This limitation has fueled human imagination for generations. It has inspired countless stories of spaceships that can break this rule, that can leap across the galaxy in the blink of an eye. But what if there was a way around this rule? What if we didn't have to break the law of physics, but instead we could bend it? It was this very idea, this hope for a cosmic shortcut, that has led to one of the most exciting and mind-bending concepts in modern physics, the warp drive. To truly understand our predicament, let's talk about scale. The distances in space are almost impossible for our minds to grasp. The moon is our closest celestial neighbor, and it took the Apollo astronauts about 3 days to get there. Mars, the next planet out, is much farther. A trip to Mars, one way, would take about 7 to 9 months with our current technology. That's a long time to be cooped up in a small capsule. But these are just trips within our own cosmic backyard, our solar system. When we start to think about traveling to other stars, the numbers become truly astronomical and utterly discouraging. The nearest star to our sun is Proxima Centauri. It is about 4.2 light years away. A light year is the distance light travels in 1 year. Since light travels at about 300,000 kilometers per second, 1 light year is a very, very long way. About 9.5 trillion kilometers. If you were to travel in our fastest space probe, the Parker Solar Probe, which can reach incredible speeds, it would still take you over 6,000 years to get to Proxima Centauri. That's longer than all of recorded human history. It's a journey that is simply not possible for humans with the technology we have today, and Proxima Centauri is just the closest star. Our galaxy, the Milky Way, is about 100,000 light years across. It contains hundreds of billions of stars. Faced with these impossible distances, humanity did what it does best. It began to dream. For decades, science fiction writers have imagined incredible solutions to this problem. They gave us spaceships that could jump into hyperspace, fold space like a piece of paper, or travel through mysterious wormholes. These concepts have become staples of our favorite space stories, from Star Wars to Star Trek. One of the most famous and beloved of these science fiction ideas is the warp drive from Star Trek. The command "engage" from Captain Kirk or Captain Picard is iconic. It signals the moment the Starship Enterprise stretches space itself and streaks across the galaxy at speeds far exceeding that of light. For a long time, this was pure fantasy, a clever plot device to make galactic storytelling possible. But then, something unexpected happened. In 1994, a theoretical physicist named Miguel Alcubierre was watching Star Trek. He was a fan of the show, but he was also a scientist who knew Einstein's equations of general relativity inside and out. As he watched the Enterprise zip between stars, a thought occurred to him. What if the warp drive wasn't entirely impossible? Alcubierre went to work on the mathematics. He wasn't trying to build a starship in his garage. He was simply exploring a theoretical possibility, a what-if scenario grounded in real physics. After weeks of intense work, manipulating symbols and solving equations, Miguel Alcubierre found what he was looking for. He had derived a solution to Einstein's field equations that described exactly what he had envisioned. The solution, which he published in a scientific paper in 1994, became known as the Alcubierre metric. It was a precise mathematical recipe for a warp drive. The paper described a warp bubble that would enclose a flat, undisturbed region of spacetime where a spaceship could sit comfortably. The walls of this bubble would be where the magic happened. The front wall would contract spacetime, pulling the destination closer. The back wall would expand spacetime, pushing the starting point further away. The result was astonishing. The bubble, with the ship inside it, could be propelled forward at any arbitrary speed. It could travel 10 times, 100 times, or even 1,000 times the speed of light. And it did so without violating Einstein's cosmic speed limit. The spaceship inside the bubble would feel no acceleration and would experience no time dilation. The crew would effectively be on a cosmic conveyor belt, moving from one point in the galaxy to another, while remaining perfectly still in their own local patch of space. Alcubierre had successfully translated a science fiction concept into the rigorous language of theoretical physics. So, how does the Alcubierre drive actually work? The idea is both simple and profoundly strange. It all comes down to a key concept in Einstein's theory of general relativity. Spacetime is not a fixed, empty stage where events happen. Instead, spacetime is a dynamic, flexible fabric. Think of it like a giant, stretchy rubber sheet. If you place a heavy object, like a bowling ball, onto this sheet, it will sink down, creating a curve. This curvature is what we experience as gravity. Smaller objects, like marbles rolling nearby, will be drawn into this curve and circle the bowling ball. This is how planets orbit the sun. The Alcubierre drive proposes to take this idea of bending spacetime to an extreme level. Imagine you could somehow pinch the rubber sheet in front of you and pull it towards you, while at the same time pushing the sheet behind you away. You haven't moved on the sheet, but the destination point on the sheet is now much closer. This is the fundamental trick of the Alcubierre drive. It doesn't try to move a ship through space, it moves space itself around the ship. This is the ultimate loophole in the cosmic speed limit. Perhaps the best way to visualize the Alcubierre drive is to think of a surfer on an ocean wave. A surfer doesn't swim through the water at incredible speeds. That would be exhausting and slow. Instead, the surfer positions their board just right and lets the powerful energy of the wave do all the work. The surfer is essentially stationary relative to the small patch of water directly under their board, but they are moving very quickly relative to the beach. The Alcubierre drive works in a very similar way. The spaceship is the surfer, and the warp bubble is the wave. Given the monumental challenges of energy, exotic matter, causality, and a dangerous arrival, the Alcubierre drive seems impossible under our current understanding of physics. The first and perhaps most staggering of these is the energy requirement. Creating a warp bubble, even a small one, would require an amount of energy that is difficult to comprehend. The initial calculations were truly astronomical. To create a bubble large enough to hold a small spaceship, Alcubierre's original paper suggested you would need more energy than is contained in the entire observable universe. This wasn't just a difficult engineering problem, it was a physical impossibility. However, science rarely stands still. Over the years, other physicists took up the challenge. Scientists like Chris Van den Broek and Harold Sonny White proposed modifications to the shape and thickness of the warp bubble walls. Instead of needing the energy of the entire universe, later models suggested it might be possible with the energy equivalent to the mass of a large planet like Jupiter. This was a huge improvement, but it's still a mind-boggling amount of energy. Converting the entire mass of Jupiter into pure energy is far beyond anything we can imagine today. Even if we could somehow generate the energy of a planet, we would still face another, perhaps even more fundamental problem. The Alcubierre drive doesn't just need a lot of energy, it needs a very specific type of energy. As we discussed, to create the expansion of space-time behind the ship, the equations call for something called exotic matter. This isn't just matter that is rare or hard to find. It is matter with physical properties that seem to violate the known laws of nature. Specifically, it must have a negative energy density, which means it would have to have negative mass. It would be matter that repels gravity instead of attracting it. All the matter we know, from the smallest atom to the largest galaxy, has positive mass and positive energy. Now, it's true that some strange effects in quantum mechanics can create tiny, fleeting regions of what looks like negative energy. For example, the Casimir effect shows that two parallel plates placed very close together in a vacuum will be pushed together by quantum fluctuations. However, these effects are incredibly small and localized, so the warp drive presents us with a chicken and egg problem. To build the engine, we need exotic matter, but exotic matter has never been found, and many physicists believe it cannot exist in any stable form. So where might these new rules come from? Many physicists believe the answers lie hidden in the strange world of quantum mechanics. One such phenomenon is the quantum vacuum. We used to think of empty space as truly empty, a void of nothingness. But quantum field theory tells us that empty space is actually a bubbling, fizzing sea of virtual particles that pop in and out of existence for incredibly short moments. This quantum foam is where some scientists see a glimmer of hope. However, some researchers, like Dr. Harold Sonny White at the Limitless Space Institute, are actively investigating if these quantum effects could be amplified. They are conducting experiments to see if they can create tiny, measurable warp bubbles in a laboratory setting. Dr. White's team has designed what they call a Casimir cavity, a device that tries to manipulate the density of virtual particles in a specific way. If they could demonstrate that they can create a persistent region of negative energy density, even a tiny one, it would be a monumental breakthrough. It would prove that the impossible ingredient for the Alcubierre drive is not impossible after all. This research is highly speculative and on the very fringes of known science. Many physicists are skeptical that these quantum effects can ever be scaled up to the levels needed for a macroscopic warp bubble. While some scientists are trying to create the conditions for a warp drive in the lab, others are looking to the heavens for clues. They reason that if faster-than-light travel is possible, we might not be the first civilization to figure it out. The universe is ancient, and our galaxy is vast. If another intelligent species had developed warp drive technology, they might be using it right now. Could we detect the signature of a warp drive in action? This is a new and exciting branch of the search for extraterrestrial intelligence, or SETI, moving beyond just listening for radio signals. A warp bubble, as it travels, would bend light around it in very specific ways. A team of researchers has proposed that we could search for these signatures in astronomical data. A passing warp ship might cause a background star to briefly brighten, change color, or even split into two images in a unique pattern. Furthermore, the act of turning a warp drive on or off would likely release a massive burst of energy. The dangerous arrival problem we discussed could have a silver lining. The gamma-ray burst from a ship dropping out of warp might be detectable across vast cosmic distances. Some scientists have suggested searching through data from gamma-ray telescopes for unexplained, transient flashes of energy that don't match any known astrophysical phenomena. So, where does this leave us on our journey? Is the warp drive, this incredible idea born from science fiction and nurtured by theoretical physics, a real possibility, or just a fantastic dream? The honest answer for now is that it remains firmly on the science fiction side of the line. The obstacles we have explored, the colossal energy requirements, the need for impossible-seeming exotic matter, the paradoxes of time travel, and the danger of a destructive arrival are not minor technicalities. They are monumental barriers rooted in our most fundamental understanding of the universe. Overcoming them would require breakthroughs that we can barely even imagine today, and yet the story is not over. The Alcubierre drive is no longer dismissed as pure fantasy by the entire scientific community. It has become a subject of serious, albeit speculative, research. It serves as a powerful thought experiment, pushing physicists to probe the absolute limits of general relativity and quantum mechanics. The very existence of a mathematically valid solution for a warp drive within Einstein's equations tells us that the universe might be a much stranger and more wonderful place than we currently know. It's a crack in the door of what we thought was possible. Ultimately, the quest for a warp drive is about more than just technology. It speaks to something deep within the human spirit. It is the same drive that pushed our ancestors to cross oceans, to climb mountains, and to set foot on the moon. It is a relentless curiosity, a desire to see what lies beyond the next hill, and a refusal to accept that we are forever confined to our cradle. The vast distances of space are perhaps the greatest challenge humanity has ever faced, and the warp drive represents the boldest possible answer to that challenge. It is a statement of hope against the crushing scale of the cosmos. Even if we never succeed in building an Alcubierre drive, the pursuit of this idea is incredibly valuable. The dream of the warp drive also serves as a powerful source of inspiration. It ignites the imagination of the next generation of scientists, engineers, and explorers. It encourages young minds to ask big questions and to believe that the future can be grander and more exciting than the present. This sense of wonder is the fuel of scientific progress. Without big dreams, we would never make big leaps. We stand today in a similar position to people in the 19th century looking at the dream of flight. Yet, through persistence, imagination, and a deeper understanding of the laws of nature, the Wright brothers proved them wrong. The warp drive is today's version of that dream. It is a horizon of possibility, a distant shore that we can see in our imagination, even if we don't yet know how to build the ship to get there. So the warp drive remains a dilemma, a beautiful theory caught between the rigid laws of known physics and the limitless potential of the unknown. The dream itself, the dream of sailing between the stars on a wave of space-time, is a dream worth chasing. It is a reminder that the universe is full of mysteries and that the human journey of discovery has only just begun. The stars are waiting,